In this video, we're going to go over the problem-solving worksheet. If you haven't done this worksheet, then you might want to give these problems a try before I go over them. So feel free to pause the video at each point and think about the problem just for your own practice. For the first question, a farmer has a daughter who needs more practice in mathematics. One morning, the farmer looks out in the barnyard and sees a number of pigs and chickens. The farmer says to her daughter, "I count 24 heads and 80 feet. How many pigs and how many chickens are out there?" Now, you might have thought about this in different ways, and there are different approaches to solve this problem. I'll show you one that's very fast and very mathematical. One way to think about it is that, first off, pigs have 4 legs, chickens have 2 legs. So every animal has at least 2 legs. With that said, what I would do first is do 24 times 2. That's 48 legs taken up. So 48 legs show up if you put this on 2 legs per animal. Now that you've used up 48 legs, let's see how many legs remain. Well, there's 80 legs total, and 48 of them were used up, so you now have 32 legs remaining. And keep in mind, what you've done is you have put 2 legs on every animal. Now the pigs have 4 legs, so these 32 legs belong to the pigs exclusively. They've already got 2 legs attached to them, and so these 32 are the additional 2 legs per animal. With that said, if I do 32 divided by 2, that will tell me that there are 16 pigs. With that said, there are 24 minus 16, which would be 8 chickens. Now, you might want to double check and just make sure that this adds up to 80. So if I do a check on this, I would say 8 chickens times 2 legs plus 16 pigs times 4 legs. That's 16 plus 64 is equal to 80. That works. Now, this is one approach that's kind of a fast, easy approach as far as doing it mathematically. 16 pigs and 8 chickens is what you get out of this. But there's more than one way to pull this off. Another approach you may have tried is just simply a guess and check. You might have started with 12 chickens and 12 pigs and done a computation similar to this one. If you do a computation and see that it's too few of legs, you should get more pigs and fewer chickens. And if you keep doing that, at some point you'll arrive at 16 pigs and 8 chickens. If you ever had too many legs, then take away a pig and add a chicken, and so on. So once you do that, then you could get this guess and check approach. Let me show you one interesting approach that I've seen before. This is a really elementary approach in that you can actually show this to a small child. You might want to make the numbers smaller, but this idea really works well. If you came up with this idea, keep in mind this does not make you an elementary thinker. It actually means that you can think like an elementary schooler, which might be something good for a teacher. Keep that in mind. So with that said, I'm going to just draw a picture. I'm going to draw 24 circles to represent the animals. Think of them like heads, if you will. Now let's put legs on these animals. Every animal has at least 2 legs, so we can add legs to the animals. Sorry, one of them I think got a broken leg. My bad. But now that we've got 2 legs on all the animals, we could count up how many we've done. If you're doing this in the really elementary way, you would simply count 1, 2, 3, 4, 5, 6, 7, 8, and so on, and you would get to the 48 legs that you've used so far, which, by the way, was what I did right here. And then what you would do is you would say, okay, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, and then just keep going and going. Once you get to 80, and you've actually counted up to 80, you can see that there are 16 circles, or animals if you will, that have 4 legs, and 8 that have 2 legs. Therefore, there are 16 pigs and 8 chickens. The next question is arrange the numbers 1 through 9 into a square subdivided into 9 smaller squares like the one shown below so that every row, column, and main diagonal has the same sum. So what that means is you need to carefully put these numbers in such a way that all these sums are exactly the same. Remember, a sum is just adding numbers together. So there's a strategy to this. First off, you might want to try to figure out what value would that be. What would that sum have to be? So let me give you a little idea of this. I'm just going to put these numbers in without any regard to the sums. Obviously, they're not going to be the same because the top row is a 6 and the bottom row is like 24 or something. It's way too big. But if I were to actually do this, now those are way off. But if I add these numbers together, I get 21 plus 24 is 45. Now that number might be meaningful. 45 is the sum of the 3 row sums. So in order for this 3 rows to be the same, it would have to be that this is your row sum. Regardless of how you put it together, 1 through 9 is going to add to 45. And so you want the 3 rows to have the same sum. And so that sum must be 45 divided by 3, which is 15. So now we know our row sum. The next step you might take is figure out what number goes in the middle. There's a few different approaches to this, and I'll show you the approach that is really concrete. You can write out all the possibilities of numbers that add to 15. My preferred method is start with the largest number, and keeping in mind you cannot have repeats, let's just say what's the next largest number that I could use here? It looks like I could use a 5, and that'll give me 14, and then I'll have to add 1. Okay, so then maybe I could try the 9, and then instead of using 5 I could use 4 and 2. And there's really not any other possibilities. You could do, say, 9, but then 3 and 3, those would be the same. That doesn't work. So there's really no other possibilities involving the 9, and the order doesn't matter or anything, so 9 is done. Let's go to 8. For 8, I could use 6 and 1, and then maybe I could go in and say 5 and 2, or this time I get 3 of them. I could do 4 and 3, and that would be all of my 8s. All right, let's try 7. For 7, I could do 6 and 2. Looks like that's all I'm going to get out of that one. I can't use 7 again, so I'll have to use 6 and 2. Or I could use 5 and 3. That would work, but I can't use 4 and 4. And then if I try to do 6, I could use 5 and 4. And then at this point, there's really no other way to write out your sums in some sort of decreasing order like I've done it. If you try to do any other ones, you're just going to have a repeat of some kind. So these are all possibilities. Now, I point your attention to the number of times various numbers occur. 1 occurs in 2 places. 2 occurs in 3 places. 3 occurs in 2 places. 4 occurs in 3 places. 5 occurs in 4 places. And in general, you'll notice that odd numbers besides 5, they show up 2 times. Even numbers show up 3 times. And then you've got the number 5 that shows up 4 times. Now, it's probably kind of obvious that if the number 5 shows up in the most sums, it should be in the middle. But I can argue it even further than that. There's only one place where you have 4 different sums, and that's in the center. This one, and both diagonals. So 5 is the only number that could be in the middle because it shows up in 4 sums. Now, the odd numbers can only show up twice, and the even numbers can only show up 3 times. So with that said, the even numbers will have to be in the corners because they show up in a row, a column, and a diagonal. So I'm just going to put 2, the smallest even number here, which means it would have to be paired with 8. And then I have another choice. let's just put 4, and then 4 would have to be paired with 6. And now from here, you can just finish it. 2 and 4 make 6. That means this number is going to have to be 9 for 15 to be in this row. 2 and 6 make 8. That means 7 is going to have to be in this row in order to get 15. And then there's only 2 left. 9 plus 5 is 14, which means I need a 1. 7 plus 5 is 12, which means I need a 3. And if you check all possibilities, you will see that all rows, columns, and diagonals add up to 15. And this is the answer. Your answer could be a rotation of this, or possibly a reflection as well. But if you look around, you'll see something similar in all possibilities, that 5 is in the middle, even numbers are on the diagonal, and odd numbers are on the places touching the middle. Here's another interesting question. Take any number and add 15 to the number. Now these are your classic arithmetic games. You start with a number and then you do some operations on it. So after we add 15, we'll multiply by 4, then subtract 8, then divide by 4, then subtract 12. And you'll write down your answer. Now given the answer, your professor can tell you the original number. And the question is, how did your professor find the original number so quickly? Let's do 2 examples, and I'll just write them down so that we can look at them and analyze them. I'll do the number 3 first. When I did mine, I added 15 and got 18. Multiply by 4, I get 72. Subtract 8, I get 64. Divide by 4, I get 16. Subtract 12, I get 4. So I started with 3 and ended up with 4. Let's try another number. Let's do 10. When I started with 10, I ended up with 11. And you could do more examples, but I want to point out what's really going on here. There is an interesting pattern. Now the pattern I think is clear. Maybe you might need to do one more. But the pattern is that if you start with a number, your final answer will be 1 higher. So if your professor can tell you your original number, you tell him the 4, he's going to tell you your original number was 3. You tell him the 11, he's going to tell you the original number is 10. That's because the professor knows the pattern. The professor subtracts 1 to get your original number. That's all there is to it. But let me show you a little bit about why this works. I want to point out that from the 18 to the 16, we simply subtracted 2. And from the 25 to the 23, we simply subtracted 2. So I'll explain why the minus 2 works, but notice that we subtract 2, and then we subtract 12, but we added 15. 15 minus 2 minus 12 is 1, so that's why it really just adds 1. Now why is it subtracting 2, you might ask? Well, notice the times 4 and the divided by 4 cancel each other out, but something happened in between. You more or less scaled when you multiplied by 4, you subtracted 8, but then you unscaled by dividing by 4. So the minus 2 comes from a scaled version. If you were to divide the 8 by 4, you would actually see that when you subtracted 8, you were actually subtracting 2 from this number here. It was simply multiplied by 4 and then divided by 4 to mask the fact that you were subtracting 2. So we simply add 1 each time. Here's one other way to look at this. Take the number, add 15, multiply by 4, subtract 8, divide by 4, and subtract 12. Very algebraic looking, but this will make sense in a moment. If I distribute the 4, I get 4n plus 60 minus 8, then the divided by 4 and the minus 12. 60 minus 8 is 52. And now if I divide both terms by 4, I get n plus 13 minus 12, and you can see that turns into n plus 1. Algebraically, that says, oh yeah, this is definitely just adding 1. If that part was a little bit confusing, just focus on the pattern. You're just taking the number, and every time you do it, if you do it enough times, you see you're just adding 1 each time. So the professor will subtract 1 to get your original number. Checkerboard question. How many squares are there in an 8 by 8 checkerboard? Now, If you answered 64, you thought at the most basic level of trying to solve this problem. You want to get used to thinking outside the box a little bit. There are a lot more than 64 squares. There are 64 small squares here. If you answered 65, then you got a little bit closer because you counted the big square. But there's actually a lot of different sized squares. Let me just give you an example. There's a square. It's a 2 by 2. Here's a square. It's a 3 by 3. And there's a lot of squares of this shape. So let me argue how this works. 1 by 1 squares, I think everyone is in agreement that there are 64 of those. But I want to point out that that would be 8 times 8. So then, the 2 by 2 squares, what it really is there's 1, 2, 3, 4, 5, 6, 7 2 by 2 squares along the bottom row. Similarly, there would be 7 2 by 2 squares along the first column. So overall, there would be 49 squares of the 2 by 2 size. Now let's talk about the 3 by 3 size. I've already got the first one drawn. And then you've got 2, 3, 4, 5, and 6 along the bottom row. And similarly, you would have 6 along the first column. So we're in the same boat. 6 by 6 gives me 36. And you can probably see the pattern at this point. So let's just fill downward. For the 4 by 4 squares, you would expect to see 5 along the bottom row and 5 along the first column, which gives you 25 4 by 4 squares. Similarly, you would get 16 5 by 5 squares. And if you continue this process, you would see 9 6 by 6 squares, 4 7 by 7 squares, and 1 8 by 8 square, which, by the way, that's the outside square, so that sort of gives you a check on this. All right, if you just add up all of these together, you would get 204 squares. Next question. If the number of rows and columns is doubled, so that you have a 16 by 16 board, is the number of squares doubled? There's a pretty straightforward way of saying absolutely not. So let me just show you a little picture. Here's 4 boards stacked together. Now I mean that when I say it. It's 4 boards that you'd have to put together to get the 16. The 8 by 8 board doubles in 2 dimensions, so even the number of single squares, you would have 64 small squares in here, but you ended up with 4 times as many squares just counting the 1 by 1s. That's fairly large. So let me just mention, of the 1 by 1 squares, there are 256. And that is way more than double. It's actually 4 times. Now let me point out some other things. All the numbers that we calculated previously will get multiplied by 4, but actually they get multiplied by even a little bit more. So imagine a 3 by 3 square. It's possible it could cross over a line. It's possible it could cross over even the center of these boards. It is possible that you could have squares of sizes that you had before that not only lie contained within an original square, but could cross over. This increases the numbers quite a bit, even more than 4 times for, say, the 2 by 2 squares. So the pattern, if you were to follow it all the way through, would be this. I'll let you read it all on your own. But the idea is this is the same exact thing that I was doing before. This number gets very large. It actually comes out to 1,496 squares. So compared to the 204 squares that we had before, this is more than 7 times bigger than what we originally had. It is far more than doubled. Last question. We want to figure out what is the pattern and what we would expect the number of regions to be for 6 points. Now there were a little bit more parts to this question, but I want to go through the gist of what it does. First off, make sure that you draw in all the lines when you do this. With 2 points, we get 2 regions. With 3 points, we get 4 regions. With 4 points, we get 8 regions. Now, if you're not careful, you're going to mess up right here in drawing in the lines. So let me show you how to draw in all the lines and make sure you don't miss any. Start from 1 point and draw a line to every single other point. Then go to the next one. He's got a line to him, but otherwise, I need to draw lines to every single other point. Then go to the next one. Draw lines to the points he's not connected to yet, and then this last point is here. If you count this up, you'll actually get 16 regions, if you did this one correctly. 6 points is similar. Where you get this. Now, one thing that's going to differ from person to person is right here. Depending on how you draw it, you may see a small triangle, like I got, or it might be that these 3 lines perfectly coincide as one. Either way, you should have either 30 or possibly 31 regions. In my case, I'll count that little tiny triangle and say that there were 31 regions. So here's the moral of the story. What did we expect the number of regions to be? If we were just to look at the pattern, 2, 4, 8, 16, it's doubling. It's just doubling the number of regions. So the expectation was this doubling pattern, and I would expect 32 regions when I do this. 32 regions. But I didn't get 32 regions. So the pattern is not doubling. There's something different going on here, and it's actually pretty complicated. It turns out to be a 4th degree polynomial on the number of vertices. It's kind of complicated. What is the lesson here? That's the question that was asked on the worksheet. The lesson is this. Don't assume a pattern works unless you know why it works. Patterns don't always do what you think they're going to. You really need to make sure you see why it works. If you're not sure, don't use it.